Hello everyone, and welcome to the General Depth First Search lecture. So in this lecture, again, we're just going to get a general overview of DFS, and then afterwards we're going to do a full live code walkthrough implementation of a graph and node class, a BFS, and a DFS. We haven't seen BFS and DFS live coded out yet, we've just seen images of example code. In the next lectures following this one, we're going to actually live code them out, explain all the steps you need, and then those are going to be your interview questions as well, as to implement each of those. So previously, we discussed the Knight's Tour, and the Knight's Tour is actually a special case of a depth-first search, where the goal is to create a deepest depth-first search tree without any branches. So that makes sense because for the Knight's Tour, we wanted to visit each node exactly one time without going back to any other nodes. So that would be your deepest DFS tree. The more general depth-first search is actually a little easier. Its goal is to search as deeply as possible, connecting as many nodes in the graph as possible and branching where necessary. So it's actually even possible that a depth-first search will create more than one tree. When the depth-first search algorithm creates a group of trees, we're actually going to call this a depth-first forest. And as with BFS, our depth-first search makes use of predecessor links to construct the tree. So in addition to that, the depth-first search will make use of two additional instance variables in the vertex class. That's going to be the new instance variables discovery and finish times. So this is just for the code that we're going to see later on in this lecture, that these two instance variables are going to be useful to us when we're trying to implement DFS. The discovery time variable tracks the number of steps in the algorithm before a vertex is first encountered, and the finish time is the number of steps in the algorithm before a vertex is colored black. So this is essentially what the code looks like. Here we have the entire DFS graph function or class object, and we have two methods in it. Besides the initialization method, we have DFS and DFS visit. Don't worry too much about this code itself. We'll actually implement this later on, or a version of this later on. But what I want to do is just briefly explain what this code would do as an example of a DFS. So we have these two functions or methods inside the class, DFS and DFS visit. And this implementation is basically an extension of a graph. So notice that it's inheriting a graph here. So this implementation extends the graph class basically by adding a time instance variable and then the two methods DFS and DFS visit, which we see here. So looking at this line right here, so for a vertex in self, which is zoomed in here, for a vertex in self underneath the DFS function, you'll notice that the DFS method iterates over all the vertices in the graph, calling DFS visit. So DFS visit is essentially a helper function for DFS. And the reason we iterate over all the nodes rather than simply searching from a chosen starting node is to make sure that all the nodes in the graph are considered and that no vertices are left out of the depth-first forest. So it may look a little unusual to see the statement for a vertex in self, but remember that in this case, self is an instance of the DFS graph class, and iterating over all the vertices in an instance of a graph is actually a natural thing to do. So don't worry about this kind of unusual statement of for in self. Okay, so moving on, we'll check out the DFS visit method a little closer. The DFS visit method starts with a single vertex called start vertex, and then explores all the neighboring white vertices as deeply as possible. If you look carefully at the code for DFS visit and compare it to the breadth first search, or BFS, what you'll notice is that the DFS visit algorithm is actually almost identical to BFS, except for that on the last line of the inner for loop. So DFS visit calls itself recursively to continue the search at a deeper level. So if we take a look here, it's going to be recursively called DFS visit right here. So it's being recursively called, and it's going to try to do that to continue the search at a deeper level. Whereas BFS adds the node to a queue for later exploration. And it's interesting to note that where BFS uses a queue, DFS visit uses a stack. And you don't see a stack here in the code, but it's implicit in the recursive call. So I know it's a little complicated, but don't worry about it too much. We're going to walk through the full implementation later on in a future lecture. This is just to give you an idea of what it may look like if you're trying to implement this as code. So to get a better understanding of what's actually going on, let's go ahead and try to diagram this out with a sequence of figures. So this sequence of figures we're going to see is going to illustrate a DFS algorithm in action for a pretty small graph, just A through F here. And in these figures, the dotted line indicates edges that are checked, but the node at the other end of the edge has already been added to the depth first tree. And in the code that we previously just saw, this test is done by checking that the color of the other node is non-white. So let's take a look at this. The search begins at vertex A of the graph right here. And since all of the vertices are white at the beginning of the search, the algorithm visits vertex A, that very first node. The first step in visiting a vertex is to set the color as gray, which indicates that the vertex is being explored, and then we set discovery time to 1. Since vertex A has two adjacent vertices, B and D, so we can see the edges here connecting B and D, each of those needs to be visited as well. And then we can just actually make an arbitrary decision that will visit the adjacent vertices in alphabetical order. So then vertex B is going to be visited next. So its color is set to gray, and then its discovery time is set to 2. Vertex B also adjacent to two other nodes, C and D. So we're going to follow the same alphabetical order and then visit node C next. All right. So visiting vertex C brings us to the end of a branch of the tree. Because if we look at this, we have a directed edge, another directed edge, and then no more directed edges coming out of C. So we've come to the end of one branch of the tree. After coloring the node gray and setting its discovery time to 3, the algorithm also determines that there's no adjacent vertices to C. This means that we are done exploring node C, so then we can color it black and set the finish time to 4. All right. So again, when we visit C, we realize that it goes from gray to black because there's no other vertices coming out of it. We've reached the end of a branch. And since vertex C was the end of one branch, we can now return to vertex B and continue exploring the nodes adjacent to B. The only additional vertex to explore from B is D, because notice how the edge goes out to C and out to D. So vertex D is then explored, and we continue our search from vertex D, which then quickly leads us to vertex E. And vertex E, sorry I jumped a bit there, vertex E has two adjacent vertices, B and F. Normally we would explore these adjacent vertices alphabetically, but since B is already colored gray, the algorithm recognizes that it should not visit B, since doing so would put the algorithm in a loop, right? You would just constantly be going BDE, BDE, BDE. So it recognizes, okay, B is gray, meaning it's explored, so I'm going to go ahead and check out the white node here. And then we note that vertex F has only one adjacent vertex, C. So since C is colored black and there's nothing else to explore, the algorithm has reached the end of another branch. And then from here on, you can see that the algorithm works its way back to the first node, setting the finish times and then coloring each vertex black, or each vertex that it visits black. So it'll keep setting the finish times as we continue on and setting them black as you basically go in reverse. So these starting and finishing times for each node display a property called parentheses property. And this property means that all the children of a particular node in the depth first tree have a later discovery time and an earlier finish time than their parent. Okay, so I know that was a lot to take in. Again, you can check out the MIT Algorithms course video playlist for a further discussion of DFS. What we're going to do next is basically go back to our roots in Python and implement all of these graph nodes, the breadth first search and the depth first search, in a way that would be acceptable in an interview setting. So you can go ahead and explore these topics independently on your own if you're interested in graph theory a little more. But the basic 3 questions you're going to be asked in an interview, at least at a basic level, is going to be to implement a graph, to implement BFS, and then to implement DFS. So those are the 3 real key interview questions. So that's what we're going to cover, at least how to implement them in the next 3 lectures, and then your interview questions are just going to be asking you to repeat those independently. Okay, thanks everyone, and I will see you at the next lecture where we're going to actually implement everything we just learned.